So, dear students, so welcome back after the break. So, we are talking about the basic structure of current mirror, both BJT and MOSFET versions, and now we are going to discuss more detail about the expression of the output current and output resistance of those current mirror. So, to start with the analysis of current mirror, we do have here the circuit, which is as I said that it is having a reference current I ref, and then we do have transistor 1 here, which is diode connected, and it develops a voltage VGS, which is supplied to the gate to source of transistor 2, and then transistor 2 it is connected to the application here. So, this is the application circuit, and we like to get the expression of the current I 2 in terms of the reference current, or you can say this I 1, and then the size ratio of M 1 and M 2. Now, to start with, we do have the expression of the current I 1. Yeah, so, expression of this current I 1, which is given here. Incidentally, that is also equals to I ref, and expression of this current assuming transistor it is in saturation. In fact, this transistor it is in saturation because its drain and gate they are connected together, and its expression is given here K divided by 2 W by L of the transistor, and typically in textbook it is referred as K n dash. So, that is the transconductance parameter, and then that multiplied by VGS minus VTH of the transistor square, and then we do have 1 plus lambda into VDS of the transistor. So, likewise, we also have the expression of current for the transistor 2. So, we do have current here. It is also having very similar expression, and because of the connection here, we do have both the VGSs, they are equal, namely VGS 1 and VGS 2, they are equal. And also we do have the threshold voltage here and here, if we consider they are equal, namely VTH 1 equals to VTH 2. Then by taking ratio of these two currents, what we are getting is the expression of the current I 2 in terms of the reference current, and then W by L of transistor 2 divided by W by L of transistor 1. So, that is the ratio of aspect ratio of the two transistors, and then we also have 1 plus lambda VDS of transistor 2 divided by 1 plus lambda VDS of transistor 1. Now, we can approximate this part in terms of 1 plus lambda into VDS difference, assuming lambda 1 equals to lambda 2, and also we are ignoring the term associated with lambda square. So, if you consider lambda 1 equals to lambda 2 equals to lambda, and if we ignore the second order term associated with this lambda, so if we drop this term, then we do get this approximation, rather approximated expression of current flowing through transistor 2. Incidentally, that is also defining the current through the application circuit. Now, this part it is defined by the aspect ratio of the two transistors and also the reference current, and let me denote that by I 2 star, just to indicate that is the main part or nominal part of this I 2 current, and then we also have the additional term I 2 star multiplied by lambda into VDS difference. So, we can write this expression in this form I 2 star plus VDS difference divided by RDS 2, where RDS, this RDS 2, it is defined as 1 by lambda into I 2 star. In fact, that is the IDS of this transistor. Sorry, this is the RDS of this transistor. So, we can say that if the voltage here and voltage here, namely the drain voltage of the two transistors, they are equal. So, that makes this part equal to 0, and hence the I 2, it is nothing but I 2 square, I 2 star. So, we can say that I 2 star is it is the current of transistor 2 when the two drain voltages, they are equal. Now, in case as I said that the voltage here, it will be defined by the application, and in case if this voltage or drain voltage of transistor 2, it is different from drain voltage of transistor 1, then we will be getting this additional part of this current. In fact, if you plot the IDS of 2, or you can say I 2 versus VDS 2, and if VDS equals to VDS 1, VDS 2 is equal to VDS 1, at this point whatever the current we are getting, that is I 2 star, and then if VDS 2 it is different from VDS 1, say this is higher. So, based on the resistance, the current it will be having additional component. So, we can say that finite dependency of the I 2 current on VDS 2 is getting captured by the second term. In fact, that is well characterized by this RDS. So, this additional part, whatever the additional current we do have, that is getting represented by the second term. In fact, this VDS 2, it can be even lower than VDS 1 by almost threshold amount. So, we will discuss that in the next slide. So, in summary, what we are saying is that the expression of the application circuit current or I 2, it is given by its nominal value multiplied by plus the additional component, which is defined by the RDS. In fact, if you see this expression, this part is the I 2 star. So, this is equal to I 2 star, which is getting multiplied by 1 plus lambda into VDS 2 minus VDS 1. So, the expression of this current based on our situation, either we may consider this expression whole expression, or it may be in this form. So, in this form, if you see here in this form, we do have nominal current plus the additional current, whereas in this form we do have the nominal current multiplied by a factor which is referred as non-ideality factor. So, whenever we will be talking about non-ideality factor is essentially that is 1 plus this additional component. Of course, this VDS 2, if it is higher than VDS 1, then this will be positive, otherwise it will be negative. So, that is the expression of the output current. If I say that this is the output of the current mirror, and of course, it depends on the condition of this transistor, particularly the VDS of this transistor. If this VDS it is sufficiently high, keeping this transistor 2 it is in saturation, then only we can get this non-ideality factor, it will be small. So, it can be and as long as it is in saturation, its dependency, as I said, that it can be characterized by this RDS, which is also referred as output resistance R out. So, the expression of R out of this current mirror is which is same as, in this case incidentally this is same as RDS 2, and that is equal to 1 by lambda of the transistor multiplied by I 2 nominal, I 2 star. So, we get this resistance, it is high only when, as I said, the transistor it is in saturation, and to do so we require the VDS to be sufficiently high, namely it should be higher than its VGS, VGS of 2 and VGS of 1 both are same, minus VTH. So, as long as we do satisfy this condition, then we are getting this output resistance. So, we need to maintain this minimum voltage across this element to get this advantage, namely this resistance it is high, and if this resistance it is high, this part it will be small, or you can say that non-ideality factor it will be small. Okay. So, similar to this current mirror, similar to the current mirror using MOSFET, let we consider the current mirror using BJT transistor. So, there also, so here is the circuit. So, there also we can, first we can derive the expression of the output current, namely this current I 2 current. In fact, I 2 it is the collector current of transistor 2 IC 2, and also here we do have collector current IC 1, and then this IC 1 and I reference they do have a relationship, but we need to say that this IC 1 it is not exactly equal to I ref, because we do have some base current is flowing for transistor 2 as well as transistor 1. So, we do have IB 1 and IB 2. Okay. But before that, if you write the expression of the collector current of transistor 1 and transistor 2 in terms of VBE, the common VBE voltage, and the corresponding VCE, VCE 1 here, and then here we do have VCE 2. Assuming that both the devices are in active region of operation, we do get similar kind of expression for IC 1, which is saturation current or reverse saturation current multiplied by e power VBE by VT multiplied by 1 plus VCE divided by early voltage of the transistor. So, same thing we do have the expression of collector current for transistor 2. Now, as I said that if I consider this both the VBs are same and non-ideality factors are equal to 1 or maybe even equal, then we can take the ratio of this current and this current, where this VBE part or e to the power VBE part is getting cancelled, and that gives us the expression of IC 2 in terms of IC 1 and also in terms of the reverse saturation current of the two transistor IS 2 divided by IS 1. And in addition to that, depending on the VCE voltage, we do have this factor in the numerator and also in the denominator. Similar to the previous current mirror, here this factor it can be approximated assuming that of course, V A 1 equals to V A 2, and if we consider, if we denote that as V A, then we can write in this form, assuming then here also this approximation involves that 1 plus V A square term we have dropped. So, if I consider if we ignore the second order terms of 1 by V A, then we do get this approximation, and in this approximation what we have, it is this factor, the main factor, multiplied by 1 plus sorry, this should be VCE 2 minus VCE 1. So, in case if this VCE of the two transistors they are equal, again this part it will be equal to 0, but if they are different, then we will get a value, and this additional component of course, it depends on the value of this early voltage. Typically this early voltage it is very high, and we may assume that the IC2 it is approximately equal to this one. So, dropping this part, dropping even 1 by V A part, so we can say that IC 2 it is approximately equal to IS 2 divided by IS 1 into IC 1. Now, if you see here, the expression of this current, it is primarily depends on whatever the collector current we do have here, multiplied by the ratio of their reverse saturation current. So, we can say that whatever the current we do have, it seems that that is getting reflected here or getting mirrored there by the mirror ratio of IS 2 divided by IS 1. In fact, in the previous current mirror, the mirroring ratio it was W 2 divided by W 1 into L 1 divided by L 2. So, that was the mirroring ratio for MOSFET current mirror, whereas for this case the mirroring ratio of the BJT version, it is defined by the reverse saturation current. In fact, geometrically if we see the or dependency of this IS on the geometry of the transistor, this ratio it is, I should say, emitter to base junction area ratio. Anyway, since this current it is getting mirrored here, that is why the name suggests that it is mirroring the current based on their aspect ratio or emitter area ratio. Now, in this circuit, as I said that the IC 1 it is not equal to IREF, because we do have the two base currents IB 1 and IB 2. So, let us try to write the expression of IC 1 in terms of IREF. This is VCE 2 and this is VCE 1, as I said. So, now if I at this node, if I see the if I consider the KCL, we do have IREF equals to the collector current of transistor 1 plus the two base currents. So, now these two base currents, again it can be, say this current it can be expressed in terms of its collector current, namely IC 1 divided by beta of the transistor. So, same thing for the second transistor IC 2 divided by beta of the transistor. And then if I consider this relationship, IC 2 can be well approximated by this IS 2 divided by IS 1 multiplied by IC1. So, from that if we replace this IC2 in terms of IC1, then we do get relationship between I_ref and then ICs. So, we can say that I reference equals to IC1 multiplied by 1 plus 1 by beta 1 plus IS2 divided by IS1 into 1 by beta 2. So, now we do have so far we do have IC2 expression in terms of IC1, and then IC1 can be expression of IC1 can be placed here, namely I_ref divided by this factor to get the final current in terms of the reference current. So, in the next slide we will be doing that. So, here what we said is that the expression of IC2, it is primarily we do have this factor and then we do have whatever non-ideality factor, and then I reference and IC1 is having this relationship. So, by plugging in the expression of IC1 into this equation, what we are getting is the final expression of IC2, which is the ratio of the reverse saturation current multiplied by this reference current multiplied by 1 divided by this factor, and also we do have this factor. Again I have repeated this mistake, sorry for that. This should be IC2 sorry VCE2 minus VCE1. So, same thing here also, this is VCE2 minus VCE1. Okay. So, now if the situation it is ideal, namely if the beta is very high, so this beta and this beta if they are very high, and also if this early voltage it is very high, then we can say that IC2 it is well approximated by IS2 divided by IS1 multiplied by I reference current. So, the rest of the part of the expression, this part we can say it is non-ideality factors. It is having two factors, one is due to the early voltage, another one is due to the finite value of the beta, or whatever you say the current loss here due to the base bias. Now, this similar to the previous current mirror, we can also write this dependency part as in terms of output resistance, and this part we can say that loss due to beta. So, in the next slide we can say that in case if we get higher output resistance or higher value of this early voltage, then this factor it will be getting improvised, or this factor it will be going towards 1. On the other hand, but then this factor it will be still whatever its value it is there, it is in fact less than 1, whereas this factor it is mostly it is more than 1. Now, this factor can be taken care differently. So, we may have two possible options to improve this circuit. One is to increase the output resistance, or increasing this factor, non-ideality factor. Other one it is improving this factor. Okay. Now, coming to this factor or the effect due to the output resistance, this output resistance can be expressed. In fact, we can rewrite this equation in terms of output resistance. Probably in the next slide I do have that. Let me see. Yeah. So, here we can rewrite the expression. We can rewrite the expression of I 2 I C 2. So, we can say that this part, let you consider this part, it is I C 2 square, or sorry, I C 2 star. So, if I say that this is I C star, then we do have here I C 2 star multiplied by this factor. Again I have repeated this mistake, sorry for that. VCE 2 minus VCE 1. Okay. Now, this part can be expressed in terms of this VCE difference divided by RO2, where this RO2 it is equals to VA divided by IC 2 star. In fact, that is the collector to emitter resistance of transistor 2. So, I should say this is collector to emitter resistance of Q2. So, if this output resistance it is higher, maybe that can be obtained by a higher value of this early voltage, then you can say that this non-ideal part it will be smaller. So, we may wish to keep the transistor in active region, so that we can get the output resistance high, and as I said that this output resistance it is essentially RO2. So, we can say this R out equals to this RO2, which is having this expression. Now, we can get high value of this output resistance, which we are looking for only if we assume that the transistor it is in active region of operation. And to get that, we require minimum voltage across this transistor. So, that is the VCE. So, we can say that the VCE minimum we require, it should be higher than VCE set. And that is the voltage here, voltage across this element, we call it is maybe V2. So, this is the voltage here. So, we can see the voltage across this current mirror, it should be at least this VC set. Typically, its value it is 0.3 volt. So, that may not be a difficult one. So, the application circuit after deducting this minimum VC set, application circuit will be having a very good possible range for its own operation. So, that way you can say that this circuit is good. Now, for both the current mirrors, as I said that there are non-ideality factors, and let us try to see how those factors can be reduced or how we can enhance the circuit performance. So, if I consider say a simple current mirror as it is given here, and we like to enhance the circuit performance. When I say enhance, we like to increase the circuit by increasing its output resistance. So, to increase the output resistance, what we can do, we can place one transistor at this point to get the modified circuit like this. So, M1 and its connection remaining the same. We do have I reference here connected to supply voltage, and then we can have M2, and then we do have the application circuit here, but in between we like to place one transistor, keeping of course both the transistors. If I call say transistor 3 and this is M2, and we like to keep a meaningful DC voltage here, so that this transistor, when I say meaningful DC voltage, it is such that this transistor, this voltage, it is sufficiently high, keeping transistor 2 in saturation. And of course, on top of this we do have the application circuit. So, whatever the application circuit we do have this circuit. Now, by adding this transistor, what we can say intuitively, even if say this voltage, in this case it is changing, if I call now say VO, even if I change this voltage, maybe that is done by this application circuit, this voltage hardly it varies. Of course, I am assuming that all the devices are in saturation region. So, based on the gate bias, V bias, and the current flow here and the size here, the VGS of this transistor 3 it is set there. So, the voltage coming here, it is essentially V bias minus VGS of transistor 3, and this VGS of transistor 3, it hardly depends on the output voltage. As a result, even if say this voltage it is changing, as long as transistor 3 it is in saturation, this voltage it is not changing. So, we can say it is remaining almost constant. As a result, we can say that VDS of this transistor, it is independent of, I should say quote and unquote, of the output voltage. So, that makes the expression whatever I 2, which is W by L of the transistor divided by W by L of transistor 1 into 1 plus lambda into VDS 2 divided by 1 plus lambda into VDS 1. Now, this expression of course remaining same, but then by adding this transistor compared to the simple current mirror, what we are doing is even if you vary this output voltage, the VDS 2 it is quote and unquote unchanged. Or you can say that this current it hardly depends on this voltage here. So, pictorially, if I compare the two cases, the simple current mirror based on probably finite lambda, we do have this output current and the voltage dependency, it is having a slope. So, let you call this is output current. So, this is the output current and the voltage drop across this one is a VO, output voltage. Now, if I consider on the other hand this circuit, where we do have transistor 3, it is protecting this source voltage from the variation of the output voltage, and for that we do have the corresponding current, it is almost remaining flat. So, this is with transistor 3 and on the other hand this is simple one without M3. So, in fact, if you see the waveform, you can see that this is giving us higher output resistance or less dependency of the current on output voltage. So, indicating that R out is very high. At least compared to this one, it is very high. So, let us try to see why we call it as very high. In fact, if you see the output resistance, looking into the output port here, the output resistance, it is basically it is a cascode structure, and we have derived the output resistance of the cascode structure, which is giving us a R out equals to R d s of transistor 2 plus R d s of transistor 3 plus G m of transistor 3 and R d s of transistor 2 multiplied by R d s of transistor 3. So, because of this additional factor, this output resistance, it is much higher than this case, where this case the output resistance it was. So, this is much higher than R d s 2, which is R out of the simple one, simple current mirror, and this is the output resistance of the modified one. Since we are placing this transistor in the form of cascode, this circuit it is referred as cascode current mirror. And as I said, that main advantage here it is that we are getting output resistance it is very high. As a result, the output current it hardly depends on the output voltage here, or whatever the application circuit current, it can be well defined by this ratio. Basically, from this one we can get the current which is independent of this output voltage. The practical circuit it is having slight modification. Instead of having independent bias here, we prefer to have that bias free. So, we can place one more transistor in diode connected form in the left branch to create a bias for transistor 3. So, we can have the left branch like this. So, this is M1, which is biasing M2 here, and then we do have M3 here, M3 it is getting bias from this fourth transistor, which is also diode connected, and of course, on top of this one we do have the application circuit. So, this is rather very common circuit. Only disadvantage of this circuit over the simple current mirror is, apart from requiring more transistor, the minimum required voltage over which we can maintain this constant current, it will be higher for the cascode current mirror compared to minimum required voltage for the simple current mirror. So, in the same way, if you consider the BJT version, so there also we do have the possibility of improving the output impedance by the means of cascode structure, and here again the purpose to have cascode it is to improve the output resistance, and as you can guess that we do add one extra transistor on top of this Q2, So, let you call this is Q 3. We may have a meaningful voltage here. When I say meaningful voltage, it is basically what we are saying is that the voltage here it should be such that transistor 2 it is in active region of operation. We do have I ref, then this is connected to VDD, and then we do have the application circuit here. So, this is the application circuit and this is the output voltage, this is the current flowing through this circuit. So, for this circuit again if you analyze it can be said that this output voltage it is having hardly any influence on this voltage, or it is having hardly any influence on the VCE2 voltage. As a result, the current flow through this transistor or the final current it hardly depends on this output voltage, or you can say that the output resistance it is in this case output resistance looking into the collector it is much higher than the output resistance of this circuit. In fact, if I consider this structure which is referred as the cascode current mirror, as you can guess this the output resistance of the cascode circuit it is equal to R O of transistor 2 in parallel with R pi. So, this is of course, we have to consider R pi 3, and then we do have R O of transistor 3, then plus G M 3, R O 3, then R O 2 in parallel with R pi 3. In fact, this can be well approximated by this R pi 3 here, and so we can say this is R O 3 plus R O 2 in parallel with R pi 3, and this part GM and this one we can say it is beta 3 into R O 3, which is definitely much higher than this is much higher than R O 2, which is the output resistance of the simple current mirror. So, compared to simple current mirror, the corresponding output resistance it is much higher, and if you observe the variation or dependency of the output current for the two cases, namely simple current mirror and cascode current mirror on the output voltage VO. For simple current mirror, based on the early voltage, it may be having significant dependency, whereas for this case the dependency it will be much smaller. So, this is with Q 3 and this is without Q 3. And the practical circuit for this cascode current mirror similar to BJT, here we use one more transistor in the left branch to create a bias for transistor 3, and then of course, we do have the below transistor, and then we do have the Q 2, this is Q 1, this is Q 3, this is Q 4. and then we do have the reference current here, and of course, we do have the application circuit, it is here. Now, this is I should say more practical circuit. Now, if I compare the two circuits, definitely I am getting higher resistance in this case, but the only drawback here, it is the minimum required voltage to get this benefit, it is higher. Namely, for this case we require one VCE, or rather VCE set. So, minimum required voltage, and that is equal to VCE set here of transistor 3 plus this voltage, and in fact that voltage, if I go through this loop, it can be shown that this voltage and this voltage, they are equal. So, that is 1 VBE1. Whereas, for this simple current mirror, the minimum required voltage here, it was only VCE set. So, that is the only limitation. So, we do have a requirement here, it is VCE set plus VBE on, whereas for the other circuit, for this circuit we require only VCE set. VCE set of transistor 2. So, that is how we can increase the output resistance, and we can get the less dependency of the output current on the output voltage. So, the other factor, other non-ideality factor, namely dependency on beta, you may recall that in the expression of the final current, particularly for the BJT based circuit, there are some loss of the reference current, because it is supplying the IB here and IB here, and the relationship of I reference with IC 1, it was I reference equal to IC 1 multiplied by 1 plus 1 by beta 1 plus IS 2 divided by IS 1 into 1 by beta 2. This is the case for the simple current mirror. Now, to avoid this loss or to reduce this loss, what we can do? We can place one transistor here. We can place one transistor here, which may work as current amplifier, which is referred as beta helper circuit. So, the circuit is like this. We do have the reference current, then we do have lower one, the Q1, and also the Q2, similar to the previous case, Q1 and Q2. But in addition to that, we do have one extra transistor, which is increasing this current here. So, if the base current here, it is say IB 1 and this is IB 2, which is emitter current of this transistor. So, let me call this is transistor 5, and IE of transistor 5, it is summation of these two current. So, the current at the base of this transistor, it is I can say this is IB 5, and IB 5 equals to IB 1 plus IB 2 divided by 1 plus beta of the transistor. So, we can say that by adding this extra transistor, the loss of this current, loss of this reference current, if I say that is the loss, then that is getting reduced by this factor. As a result, the relationship between I ref and I C1, instead of this equation, in this part you will get a factor which is 1 plus beta 5. So, this is the corresponding relationship. I ref equals to I C1 multiplied by this factor and then this part. So, what is its consequence? The final expression of this I 2 or I C 2, if I say this is the I C 2, and then we do have the application circuit here. And so, it is having I S 2 divided by I S 1 multiplied by I ref, and then this factor you can see it is getting improvised by adding this 1 plus beta of transistor 5. And this part, however, it is remaining as is. Once again, sorry, this would be VCE 2 minus VCE 1. So, this part we already have discussed. To improve this one, we can put the cascode structure. In addition, we can put this transistor to make this non-ideality factor very close to 1. So, this is referred as beta helper circuit. By the beta of this transistor, we are making this factor more towards the ideal one. So, that is why it is referred as beta helper circuit. So, that is the expression of the final current, whatever you see I O or I 2. I think these are the two possible way of improving the circuit, and by doing this, as I said, that non-ideality factor, it is going close to 1. In other words, beta helper circuit, it increases the accuracy of the current. Now, to summarize what are the things we have discussed in this lecture, we have started with motivation of going for current mirror, namely to implement current biasing element in amplifier, we require current mirror. And we also have discussed about basic characteristic, namely output impedance of the current bias element or current biasing element should be as high as possible. And in addition to that, the current mirror also works as signal mirroring circuit. Later we will be talking about how it is really doing that, but just to give a hint that it also have good application in current mode amplifier to mirror signal. Not only mirroring signal, it also helps to amplify current mode signal. Then we have talked about the basic structure of current mirror, and to get the basic structure we have discussed about various versions of current biasing elements, namely simple resistor, and then leading to active device, and then we have discussed about the final version, which is current mirror. And structurally current mirror, it is having a current reference followed by a mirror pair transistor. And then after the break we have discussed more detail about the expression of the output current. So, we have gone through detailed circuit analysis, and we have derived the expression of output current of a current mirror in terms of reference current and then aspect ratio or the reverse saturation current ratio. Then we also have talked about the output resistance, and then finally we have talked about advancement of current mirror, namely cascode current mirror, and also so this is for both BJT and MOS. and then also we have talked about beta helper. So, beta helper it improves the non-ideality factor, second non-ideality factor of BJT current mirror due to the whatever the loss it was having in the base bias. So, I think that is all we have discussed. We yet to discuss one more item, small signal model of current mirror, that it will be discussed in the next lecture along with other topic. Thank you for listening.